Hello, Nandan. I'm Sai Venkatakrishnan, a PhD scholar in the Department of Computer Science and Engineering in IIT Madras. This is week 5 live session for the course Operating Systems Fundamentals. The agenda will be as follows. We will be discussing some questions with respect to the week 5 lectures, that is thread, about threads and multi-threaded concurrency, and then scheduling, the basics of scheduling. And we will be discussing some questions which ultimately will help you to solve the current assignment questions which was released for week 5 in the current offering of the course. So if you have any doubts, you can post it in the chat box, or you can unmute yourself and speak out. You can interrupt me in between and ask your doubts. So let's start with the first question. Um, Question 1, a process can be fill in the blanks. Can it be single threaded or multi threaded, or can it be both single threaded as well as multi threaded? Is there any guess, uh, Nandan? C. Okay. Yes. So a process, if you use the correct API, say if you use the pthreads library or something, and say within a condition, if some condition is met, say you are having a web server, and if initially it will be, for example, if you just have a web server process running, initially it will be a single process, say P1. Only if multiple requests are coming to it, say request 1, request 2, multiple requests comes to it, then maybe the design of the web server would be such that it creates new threads, T1 to manage request 1, T2 to manage request 2. So this web server as in would be a single process. Initially it would be single threaded, but later it can be multi-threaded also. It can become multi-threaded by using APIs like the threading libraries like pthread and all those things. So the correct answer, as you mentioned, answer C is the correct answer. The other answers or options are wrong. C, both single and multi-threaded. That's the correct answer. Okay. Uh, any doubts in this? If not, we'll move to the second question. Right. Second question is as follows. According to Amdahl's law, if the program is 100% serial with infinite number of cores, what will be the speed up? Is it 1, is it 0, or 1.3 or 1.4? I have a 100% serial program, right? And I have an infinite number of cores. Is there any way, is there any way to speed up or something? Okay. So you mentioned it is 1. Let's see how we get the answer 1. What does Amdahl's law in the first place? So Amdahl's law is nothing but it states that blindly, if you have like say n number of cores, if you just put it in your system and you just run any program, it won't result in a speed up. There won't be like not always speed up. It won't always improve the performance of your program. The only way when this n cores should be utilized properly is when the program is multi-threaded, or it's designed in such a way that you can split your program, distribute it into tasks, and run it across different cores. Then that's the only way to really speeden up your process and make use of all the cores. So Amdahl's law is as follows: 1 by s plus 1 minus s divided by n. So this S over here denotes the serial code present in your program, the percentage of serial code, and n is equal to the number of cores. Right, I can decrease my. So n equal to number of cores. Now what this thing tells is the Amdahl's law. It tells that this part over here, so 1 is the original speed of the program, which is all the serial code, like 100% serial. And now Amdahl's law tells how much speed up we will get when we uh, parallelize part of the code. So this part of the code which is parallelized is this 1 minus s. This component denotes the parallelized code, and that code we can run it over n cores. We can split it and run it simultaneously. Now, and this whole formula will tell the speed up attained by this uh, parallel code that you have designed compared to the original serial code. So if you substitute the value, so here s equal to 100% serial code. So here s equal to 1, that is 100%, and n is equal to 1, n is equal to infinity, sorry. So there are infinite number of cores. When we just substitute the values, get the speed up is equal to 1 by 1 plus 1 minus 1 divided by, sorry, 1 minus 1 divided by infinity. If you just substitute the value, you just get 1, because infinity, 1 by infinity is 0 and 1 by 1 is 1. So even if it's using infinite number of cores, based on the Amdahl's law, you cannot fully utilize all the cores since it's everything serial code and you should run it on one core. So the speed up you can achieve is equal to what you run it on one core. So the speed up is 1. There is no speed up at all. So the correct answer, as you mentioned, Nandan, option A, 1 is the correct answer. The other options are wrong. The speed up is 1. The critical thing while designing these multi-threaded programs is to keep in mind that the way we design the programs should not reduce the speed of a single threaded program. Say I design a complex multi-threaded program, and suppose I had to run that multi-threaded program on a single core, it should not reduce the speed. It should not be less than 1 actually, the speed up compared to the original serial code. So that's a tricky part, and we should make it compatible also with like a multi-threaded program for both a multi-core mission as well as a single core mission. It should run equally good, right? Any doubts in this question? Right. Okay. Sorry for the disturbance. Yeah. We'll move to the third question then. Yeah. So the third question is as follows: multi-threading on a multi-CPU mission does what? Does it decrease concurrency? Does it increase concurrency? Or doesn't affect the concurrency at all? Or it can increase concurrency in some cases and decrease concurrency in some cases. So which one of the following is the correct option? Is it option A, or option B, or C, or D? So multi-threading is, you from the same process you do create multiple threads, and on a multi-CPU machine is you can run these threads on different cores simultaneously. That's what multi-CPU is all about. So say if this is CPU 1, this is CPU 2, you can run T1 thread 1 on CPU 1, thread 2 on CPU 2 simultaneously, and all these threads belong to the same process P1. So obviously, multi-threading, if used on a multi-CPU machine, will always increase concurrency. So option B, as you have answered, that's the correct option. Multi-threading always increases concurrency, especially on a multi-CPU machine. Okay, and it increases concurrency. Hmm. Right. So option B is the correct option, and option A, the other options are wrong. And note one thing, the, the tricky part is, see, they have mentioned multi-threading on a multi-CPU mission. They have not mentioned multi-threading on a single CPU. So say a single core system, you can run a multi-threading on a single core also. The only thing is now, instead of say scheduling multiple processes, say instead of doing process scheduling, you will be doing thread scheduling actually. And running a multi-threaded program on a single core doesn't give you much improvement in performance. And the word concurrency is different from parallelism. If you have read the lectures, um, attended the video lectures, professor would have mentioned that what's the difference between concurrency and parallelism. Concurrency is it's as if uh, each thread or the process or the tasks, thread or process, we term it as a task, and the task is making some progress. When you see at some point in time, all the tasks are making progress, but it needn't be the case that all the tasks are running simultaneously, as in a multi-core system. So in a single core system also concurrency will be achieved, right? In a single core as well as a multi-core. Parallelism is different from concurrency, as in all the tasks should be executing simultaneously. To be executing simultaneously, whereas in concurrency, it would be making progress only. So how does it make progress is whether it can swap out the processes or the tasks that are executing and in a round robin fashion, and make sure that each task reaches at least half of its progress state or something. And concurrency is viable both in single core as well as in multi-core systems. But parallelism can only be done if we have a multi-core system, because the each core would be specified affiliated to one task, and to run multiple tasks simultaneously we have to do parallelism. We have to have a multi-core system. So here multi-threading really improves concurrency only if it's run on a multi-CPU machine. Say the same multi-threading was run on a single core. Say you just have a CPU 1, and for the same process P1 you have a T1, T2, uh, say you have T2, T3, three threads you have. Which thread will you run on the CPU? So this will be taken care of your kernel, and it will be rather doing a thread scheduling actually. Instead of different processes, it will select which thread to execute. Now what happens is the whole process to complete, all these threads have to complete, or those conditions have to be met. And this will increase the time taken for the process to complete actually. So this multi-threading is on a multi-CPU machine. In that case, it will always increase concurrency, right? Any doubts in this question? Right. Thanks, Nandan. Yeah. Because on this question is framed in a tricky way. When I read that question again, I just thought what will happen in a single CPU machine. So right, it becomes tricky, this multi-threading concepts and all those things. And the cool thing is you can, that's what I mentioned in the previous question, right? If you run the same multi-threading program which you had designed for a multi-CPU machine, and in some case, say like all your adult threads are occupied, your adult cores are occupied, and you couldn't run these multiple threads on different cores, then what will happen? You should run it on a single core. The algorithm, the threading has to be designed in such a way that even your multi-threaded program on a single core should know that it runs on a single core, and it should execute in such a way that the performance doesn't decrease compared to the original serial code. So that's the difficulty in forming these multi-threading algorithms and running it on different cores or single core also. Yeah, so it's an interesting concept. Yes, Nandan, uh, you had a doubt?
Hello.
Yeah,
Can you hear me?
yeah, I can hear you.
Like, so the same question is the question was multi-threading on a multi-CPU, right? So,
Yeah,
so if the question was multi-threading on a single CPU machine, it will be the answer would be B, right?
and
Increase in concurrency.
multi-threading on a multi-CPU, is answer is B. If it was on a single CPU, then mostly the answer would be option D, in my opinion. It can increase or decrease the concurrency, right? Because say you, how do you measure concurrency? You take some time chart, like say at after 10 seconds, how many processes are making progress, how much have they made progress, right? So it's a tricky question to answer, right? Because now you will be, but it in a single CPU, mostly it will be it will increase concurrency only. It actually doesn't affect concurrency in a much way in a single CPU mission, right?
So
Because
like
yeah, continue.
my question is like if the scheduling algorithm is like a round robin algorithm,
uh,
like each thread will get uh, like each thread will get its same time share, like time slice.
right.
So every process will be moving at same like speed,
Yeah,
which will be increasing concurrency, right?
which will increase in concurrency. No, so see like this, if it's just a single core and you say it's a round robin, we should see how the kernel first of all is designed at kernel scheduler, and say in round robin it's like 10 seconds every thing. Say the kernel is designed in such a way that it selects which process next to execute, selects the process in each time quantum every 10 seconds. Okay, in that case, say now it selects p1, in the next it selects p3. Now what the kernel will do is within this 10 seconds, which thread to execute. Say p1 has 4 threads. Out of this 4 threads, which one is ready to execute, that the kernel should decide. In say process p3, which thread is free to execute, that the kernel should decide. Or the user, the thread library, that should decide. So it don't affect concurrency, in my opinion, because it's just a single core only, right? How many ever threads you create in a single core, it don't it can't be executed simultaneously. It just has to execute on that single core, and it don't affect concurrency. Actually, that's the correct answer, in my opinion.
Yeah. Okay. Okay.
uh,
One more thing,
sure.
can I ask one more thing?
Yeah, sure.
So, like as you mentioned that kernel selects process, right?
Right.
Like uh, does it select the threads or like um, my question is that
Yeah.
kernel sees the
Yeah,
process as a thread or the thread itself?
yeah, so that's a nice question, Nandan. So it's up to the kernel designer, right? If the kernel is given some way of looking into the threads also, we can do it, giving some priority, thread scheduling, something like that. So there is this mapping, right, from user to kernel threads, right? So the kernel thread also has to be, so if it's like one-on-one mapped and all those things, then the kernel can select which thread to execute also. Or else the easy way is it will just select which process to execute, and from within that process it can just either give that control to the user, that threading library, whatever you use, to select some thread and run it on the CPU, or it can just select one thread among the multiple threads within that process what it had selected. So it's up to the kernel, um, the kernel designer, the, the OS developer. So you can have multiple policies. in this scheduling thing.
Yeah. Okay. Okay. Thank you.
Yeah, and that's a reason like why like multi-threading makes more sense if you run it on a multi CPU machine. On a single CPU machine, it doesn't affect much uh, the concurrency, right? Um, so, any other questions? If not, we will move to the uh, next question. Which of the following components of the program state are shared across threads in a multi-threaded program? Which of the following components are shared across threads? So say you have a process P1 and it has what's the usual state of the process? It will have a stack, it will have the heap, and it will have some data global variables, and then it will have your code. And that process, when it's executing, it will have some registers, the machine registers that it would be accessing. And now when it creates some let's say it creates 4 threads T1, T2, T3, T4. Which one of these following would be shared among all the threads? Is it the register values, the global variables, heap memory, or both B and C? Okay, Nandan has answered D, right? So register values, it should be different for each thread, because the register values are the ones that your instruction should be using. um, Say add instruction, add r1 comma r2 comma r3. So all these things, the registers would be, the instruction would be using those registers, and those are private memory. So whenever we switch between threads, say T1 to T2, these registers would be stored in a private memory on a stack or something like a thread local storage. On a thread local storage, whenever you context switch, whenever you context switch between threads, say T1 is now executing, it has to stop, now T2 has to execute, then all these registers would be stored. And now after T2 has finished executing, when it returns, when again T1 has to resume execution, similar to how the interrupt handler and trap handler occurs when the process has to resume execution, in the same way even the thread will be resuming execution by loading these registers again from the thread local storage, and then it will continue resume execution. So the register values have to be different, it is not shared. But the global variables pertaining to the data section, these will be shared across all the threads. So this is actually one advantage of threading, because for communication between threads, for communication between threads, you will be using global variables. That's an easy way, because you don't have to switch page tables, you don't have to switch memory contents or something. It's just like you write to that global variable, and some other thread when executing it can read from that global variable. But the only downside is while doing those read and writes, it should be synchronized. You don't result in a race condition or something. That's it. So these global variables, uh, excuse me, pertaining to the data section is shared. Now there comes the heap memory. Now comes the heap memory, and the heap memory is this section, and this will also be shared. So the correct option, as pointed out, it's option D. Um Both B and C. Register values should not be shared. Um but global variables and heap memory would be shared. Now, this is the case in basic, the OS design and all those things. But a subtle difference as far as this course is concerned. If in exam or any other assignment, if they ask this question, you stick with this answer, that is both global variables as well as heap memory would be shared. But in later operating systems, in some cases, right, in some corner case, some design of operating systems, the heap memory would also be multi-threaded up to some extent. So what I mean by heap memory would be multi-threaded is, say your the program, your process P1 creates 100 threads. Okay. Now the heap memory as such is shared, right? So whenever you have to heap memory is shared. Say you are doing in every thread you are doing a malloc and you are writing something, right? If you have to write something in the global memory in the shared location, you have to lock, because to prevent race condition and synchronization, you have to lock that memory cell, whatever you have to lock the memory address, and then you do the write operation. So you lock first, then you write, and then you unlock. So this is the step-by-step procedure. So to prevent, say if thread 1 is executing a malloc and then writing to a location at 1000, which is in the heap memory, and thread 2 also is wanting to write to this location, then you cannot take a chance. You should lock the memory for thread 1 to write it properly, because otherwise the contents would be invalid and it would be like corrupted. You won't know which, whether the write operation was successful or not. It's a race condition. So to access the shared memory, this locking procedure should be invoked, or some mutexes and those synchronization. This would be expensive, and imagine if you have to do this for every heap location or change in the shared memory locations. So this would be expensive. So what the designers would do is, for 10 threads, you will have a separate memory. So for every 10 threads that are created, a separate heap memory would be created. So the contention between that heap memory would be less when compared to 10 threads and the 100 threads. So not for every thread there would be a separate heap memory, but it would be shared up to some threads alone. And if the thread count increases or something, then again a new heap memory would be created, and all those tricks and design strategies are used to make the accesses less expensive and make it efficient. Okay, so these are like it depends on each heap library how it is designed, and you can make custom heap libraries and install it in your system and run your code. But this is just for your information. Like even in these ways, the heap memory would be divided between threads, and there can be multiple heap memories for each thread also. So that is the case, but the general concept is both global as well as heap memory would be shared among all the threads. That's the basic concept, right? So option D is the correct answer in this scenario. Any questions, any doubts in this question? Can a thread create a child thread? Uh, right. So that's a nice question. So can a thread create a child thread? Yes, it can create, like there is nothing stopping it from creating. It can. It just needs to call whatever that p thread create and those things, and very well it can create a child thread. Say you can run your web server itself across the request. Uh, say you are running a web server, and once a request comes in, you create one thread T1, and this T1 would say this has multiple tasks. One is for doing say Fibonacci number, one is for say doing something in the loop like that. It can create multiple threads and try to make it, try to parallelize it also to improve performance. There's nothing stopping it from using the threading library. The only thing what is custom is what's the cancellation like if this thread whether it waits for these two threads to finish completion and exit, or if this thread stops executing or something like that, if this threads get killed, T1 gets killed, what happens to the child threads, say T2 and T3, these are the child threads, whether these get automatically reassigned to this process and it continues. So those are all the design policies that the threading library has to decide. But yes, you can create threads from existing thread. There's nothing stopping it. Right. That's a nice question, Nandan. I will take note of this question and I'll add a slide at the end also while uploading the slides. And if possible, I'll add an example also of a policy, whatever is being implemented in a real world OS regarding this thread creating another child thread. Okay. So if no more questions are there, then we can move to question 5. Okay. So determine the average waiting time for the following set of processes scheduled using FCFS, first come first serve policy, and assume that the processes arrived in the order P1, P2, P3, P4 and P5. Okay, and another assumption is the arrival time for all the processes P1 to P5 is 0. So assume it to be 0, that is assume that all the processes arrived in the at the same time 0, but in some way what happens is due to the it got uh, it the since only like the process the kernel scheduler will see only one process at a time while arriving. It sees P1 coming first, P2 second, so P1 is coming first, P2 comes second, P3 comes third, P4 comes fourth, and P5 comes fifth. But the arrival time for all these things, all these processes came together, but the scheduler sees it in disorder, the process arrival. Now, and also we have been given the burst time of all these processes. P1 has a burst time. So burst time as in how much time it will take to execute, unit time. Now the question is whether it what's the average waiting time. So Nandan tells option B. Let's calculate and see whether that's the correct answer or not. Okay. So first come first served is whatever comes first. You have the scheduler will pick that and execute. And this first come first serve policy is a non-preemptive policy. So by non-preemptive, you mean like whatever comes first, I take that process. So P1 came first. So this is like a Gantt chart. We'll build it, and so this makes your calculation simpler. So it's at time 0 P1 comes, and first come first serve basis it will take P1. It came first. It will service that first, and since it's non-preemptive, it will execute P1 fully, and then once P1 is fully finished execution, then the scheduler will see which process came second after P2. After P1 which process came, and it sees that P2 has come, so it will take that process and then fully execute. So by non-preemptive, you don't stop P1's execution in between and schedule some other process to execute. So that's what non-preemptive means, and FCFS is a non-preemptive policy. So to calculate the waiting time, let's draw the Gantt chart and how the processes are scheduled and executed. So first P1 would be executed, and that will execute for 5 unit time. Next, once P1 is over, it sees that P2 should be scheduled, and that will execute for 15 units. And next P3, okay, so P3 is the third process which came, so it will execute P3, and this is for 20. Um, sorry, this is not right. Okay, so it will this will execute for 5, and P2 executes for 15 burst time, right? So sorry, this will be actually 15 plus 5, since this whole thing will be 15. So at time 20, this will stop execution. This P2 will stop execution, and now at time 20, P3 will start execution, and that will continue for 20 units of time, and that will be 40 actually, right? And that will be for 40. After 40 units of time, P4 will start execution, since this P1 has finished, P2, P3 has finished. So next P4, and that will be for again 40 units of time. So from 40 plus 40, it will be at 80 units of time, P4 would have finished execution. And now finally P5 will come for execution, and that will be for 5 units of time, so it is 85. Okay, so this is the thing, and this is the burst time. If you just minus it out and see, so this will be for 15, this will be for 20, this will be for 40, and this will be for 5. So the burst times. And now to calculate the average waiting time, it's nothing but sum of the waiting time for each process. For each process. So here I equal to 1 to 5 divided by 5. That's the number of processes, right? And what's that actually? The waiting time, how to calculate from the Gantt chart? Say P1, it is immediately executed, so it's no waiting time. For P2, you see that the starting time, when did it start execution? It is 5 units of time. So 5. For P3, if you notice, it waited for 20 units of time, and then only it starts execution. So plus 20. And for so this is for P1, this is for P2, this is for P3, and for P4 it waited for 40 units of time, and P5 it waited 80 units of time. Divided by number of processes, that is 5, 40, 20, 60. Okay, so 145 divided by 5, which is nothing but 29, right? So this is the average waiting time for each process. This is how you calculate. So the correct answer out of these three is, as Nandan has mentioned, it is 29, right? 29. The other options are wrong. So this is the correct one. Any doubt in the calculation of the average waiting time, or it how to calculate this the Gantt chart and all those things, right? Okay. Then let's move to the sixth question. Okay. If the degree of multi-programming is low, then which statement is correct? So degree of multi-programming is nothing but how many processes are executing simultaneously. That's the degree of multi-programming. They are making progress and those things. So which statement is correct if the degree of multi-programming is low? The turnaround time and the CPU utilization is low. Does it? Can we infer this when we say degree of multi-programming is low? Or is the waiting time high? Or the turnaround time will be high? Or none of the above? Or what can we tell when we say the degree of multi-programming is low? Which statement is correct? So degree of multi-programming is how many processes are ready for execution, right? They can be executed parallelly, or um, they are ready for execution. That's the degree of multi-programming. And if this degree of multi-programming is low, which statement is correct? Is it that the CPU utilization? So CPU utilization is nothing but how many, whether the CPU is fully utilized, whether every unit time something is getting executed, whether the CPU is always busy, how much percentage of time the CPU is busy, always busy or not, the percentage of time. And the turnaround time is nothing but the response, the completion time for execution. And the waiting time is when will the process start execution, right? So these are the terms that are being used, and Nandan has answered option A. Let's see. Okay, so if the degree of multi-programming is low, what does that mean? You have a less number of processes that are ready for execution in the system, that are active, ready in the system. So that is what if the degree of multi-programming. Okay, if the degree of multi-programming is low, it implies that the less number of processes are ready. If less number of processes are ready, what does it mean? One, uh, the waiting time will be less, obviously, right? Compared to a situation where many processes are there, the waiting time is low because you don't have many processes to run. So the existing processes which are ready need not wait for a long time to get executed on the CPU. So the waiting time is low, and and also, since there are not many processes and even the waiting time is low, the turnaround time will also be low. The process for completion is low. Okay, but the downside, so the waiting time is low, my time for completing one process, the average turnaround time, that will also be low when the degree of multi-programming is reduced. But whether my CPU will be fully utilized or not, CPU will be utilized or not, it depends, right? Because the number of processes that are ready is low, then all these processes, the turnaround time is low, so all these processes would finish execution in a short time, and once that is over, the CPU does not have any process to execute. So the remaining time the CPU has to sit idle, and in that case the utilization of the CPU is not done, and the CPU utilization will be low. So out of these statements, you see that option B and C are wrong. The time won't increase, the waiting time or the completion time. So option A is the correct option. The turnaround time will be low, but the CPU utilization will also be low. So this is an interesting question. So at one time, uh, at, at one thing, the advantage is the completion time is low, so the processes are more interactive. But the other end, my CPU is not utilized fully. So which should I worry about? Whether to utilize my CPU better, or but if I utilize my CPU better, it might be the case that the turnaround time might increase. So this is like an interesting trade-off when we see the degree of multi-programming that should be maintained compared to the completion time and these factors when scheduling processes. Okay, so option A is the correct option. Any doubts in this question?
Uh, Hello.
Yeah, yes, Nandan.
Uh, have a question like, does the degree of multi-programming implies concurrency?
The degree of multi-programming, it tells how many processes are ready for execution, and yeah, in a sense, it so concurrency is all about making progress, right? How many processes are making progress? The degree of multi-programming is tells the number of processes that are ready for execution, and how many are actively in the ready queue. So in a way, yeah, it in a way it is somewhat related to concurrency, but not directly. Let's say the process is ready, but it has still not made any progress. It's just waiting in the ready queue. So that doesn't make it concurrent, right? That process which is waiting, like the waiting time is high. So yeah, but it is more or less related to concurrency, yes, but not directly.
Thank you. Yes. Thank you.
Yeah. So I'll add this question also to the slide. One. It's a nice question. So okay. So I'll move on to the seventh question. So which algorithm is defined in time quantum? So we have a set of algorithms, uh, shortest job scheduling, round robin, priority scheduling, and all those things. Which of these algorithms is based on the notion of time quantum? That's it. Okay. So B is the correct answer. So round robin scheduling is the one where for a specific time quantum you just circle between all the processes and execute each process for the time quantum, and it's a preemptive scheduling, because irrespective of whether that process finished or not, if the time quantum has is reached and still the process is not finished, then you stop that process and get the next process to execute. So it's preemptive scheduling, round robin, and it's based on the notion of time quantum. Right. Any doubts in this question?
Hello.
Yeah. Yes, Nandan.
I have read that in the preemptive scheduling, there can be race conditions, right?
Right. Yes, there can be.
Uh, so, like, uh, in the non-preemptive scheduling, is there any race conditions?
In the non-preemptive scheduling, whether there can be race conditions.
Like, let's say there are four cores.
Okay.
Four cores uh, are trying to like update a shared value. Uh, there can be race condition, right?
Okay, so one thing, right, in scheduling, as far as what we are learning now, everything happens on a single core, and this is between multiple processes or multiple tasks, let's say. Okay, and the scheduler will be running for each core separately, as in the scheduler, whether it can be core aware, right? So the scheduler can it can select a different process for this core, okay, and it can have a separate list for this core, and core 2 it can have a separate a round robin list and those things. And as far as your question is concerned, if you get the notion of multi-core, okay, there is always the possibility of race condition, whether it's preemptive scheduling or non-preemptive, there is always the possibility of running a process, say P1 and P2 on both simultaneously on both the cores, and if both access the same data, then there is always the possibility of race condition. But now if you just have a single core only, and now you are just running a preemptive round robin algorithm, and you switch between P1 and P2, then also there might be a race condition. But if it's non-preemptive, then it's the race conditions won't be there. First P1 and then P2. So the race condition won't be there in a non-preemptive. But when you specify it clearly, like there are 4 cores and 2 processes, then irrespective of your scheduling algorithm, there will be a race condition possible.
Uh, so like in case of single core also, like at a time instance only one process is running, right? So like
Yes.
how can be a race connection be occurred? Only one, like
In which case,
only one thread will
this or this case?
single core
Okay.
in a preemptive.
Okay. Say it depends on how the um, at what point the preemption occurs. Say P1 is about to enter the lock or something, it has changed the lock variable or those things in between this locking mechanism that P1 has entered, and now at that point the preemption occurs, and now it switches to P2, and now P2 tries to get the lock or something, and the locking mechanism has not fully finished or something like that. Assume the locking mechanism, whatever, like setting that variable to 1 and setting some other variable to 1, it means that variable, that part of the memory is locked. Assume that the way the locking mechanism works. Then in that case, it will be like you cannot tell deterministically what happens. The thing to note is at what point my preemption occurs when P1 is entering a lock. Is there some way to mention, like, okay, like when I'm executing this locking mechanism, I make sure that the process one, that executing process, successfully either gets the lock or it doesn't get the lock. Only after knowing this outcome, the preemption, it should be preempted, right? In that case, it makes the logic more uh, deterministic, because these locking variables are all shared, right, between these processes, and this locking mechanism, if it goes and disturbs some of the locking variables partly, and the remaining before executing it fully, that locking mechanism, the process P1 gets preempted, then the P2 process would be in a dilemma whether it's locked or not, right? So that's based on the logic that we use for this locking and synchronization, and this type of confusion while doing locking mechanism, it's like non-deterministic and becomes tough to argue whether it will succeed in locking it properly or doing this or not. So that is that's what we tell, like preemption might result in race conditions or deadlock. Say like if P1 entered a loop where it is waiting for P2 to send some data, and at correct time P2 starts executing, and P2 before sending P1 that data, it has to send it's waiting for some data from P1. So what happens now, like P1 and P2, it will just be alternating and there won't be any progress. So these type of deadlocks, like these race conditions occur usually in preemption. Whereas if it's just like non-preemption, so you just execute that process fully, and then you take the next process, then these uh, race conditions, these things don't occur usually.
So like if a process, if the P1 process get the lock, then we don't have any race conditions, right?
Right. So
Yeah.
the locking mechanism that how so those if I get, even in Intel processors or something, few instructions are like serialized instructions or something that tell no, not serialized, sorry, atomic instructions. So in Intel x86, if you see, there are some instructions like LCK, if I'm sure, LCK, like lock something. So usually like add instruction is just like adding two registers. But if you see, to lock a memory region, you would be incrementing some status telling I'm which thread is accessing that variable or something, which process, and you will be setting some variable to one, that mutex or semaphore, some those things to one, and like that. So these all these operations should be atomic. Atomic as in either all of this should happen, or all of this should not happen together. So it's not like okay, out of these three steps in locking, first two happened, but the third one before I executed, the process got preempted. That should not be the case. Either this full all these three steps, one, two, three, all these three steps should happen together. Then it means that process P1 has locked successfully. Otherwise, all these three steps should not happen at all. Then it means that process P1 did not lock, could not get the lock. So this is what an atomic instruction, and x86 there are some instructions for this synchronization and those things, and having it as instructions that are supported by the hardware itself, right? You get more speed and efficiency, and it's easy to reason about. So you can read about atomic instructions. I will share a link at the end of the slide when uploading about these atomic instructions. So this is what atomicity is all about, and yeah, when you tell like if the locking mechanism goes through properly, then yes, then there is no race condition as such. So it depends at the point where the preemption occurs. So that's the main logic. Even if you see how the interrupts should be handled, say like the interrupts. I'm not sure whether the professor mentioned this in the video lecture. I guess you would have mentioned in the interrupt handler also, some part in the kernel, at least some part of the code which gets the interrupt ID, and those things should be serialized actually. Serialized, and the interrupts are all disabled at that time. It should not be preempted. Right? Some part of the code in that interrupt handler should be atomic, and it should execute properly. So these are all some conditions where we should take care of, and the preemption occurs or at which point it occurs. This is what is the difficulty of having these preemptive algorithms and multi-threading. It just the scenarios become so complicated. You have to reason out fully every corner case and design your algorithm, right? So any doubts, Nandan? I'll add this atomic instruction, this doubt also at the end of the slide as a question.
Yeah, thank you for the
Yeah,
clarification.
yeah, okay. So if no doubt, then we'll just move to the eighth question. The eighth question is as follows: the interval from the time of submission of a process to time of completion. So what is this interval called? Is it the waiting time, the turnaround time, or response time, or throughput? So throughput is actually the number of processes that are executed per unit time, say. So that's the throughput of the CPU. Response time is first output when it is getting, when the process is getting the first output, and waiting time is the total waiting time it has to wait for each process in the ready queue. And turnaround time is the correct answer, which Nandan has mentioned. Turnaround time is the completion time, starting from time of submission to completion. So option B is the correct answer. The other options are wrong. Turnaround time is the interval from time of submission to time of completion. Any doubts in this question? Right. In that case, let's move on to the ninth question. What is a FIFO algorithm? First in, first out. Is it like so? This is actually, we can just give it like first come first served also. What we had discussed previously. Is it that the first executes the job that came first in the queue or last in the queue? Or so the answer is obvious. It's option B. That is, the process that comes first in the queue will be executed first. That's first come first serve, or that's first in first out. So option B is the correct answer. Uh, I hope no doubts in this question. If yes, then we'll move to the 10th question. Which of the following is not shared by the threads? So the same. So in the previous one of the questions, we had seen which parts of the memory is shared by the threads. That is the global and data. Now we see what is not shared by the threads. So whether it's a program counter, stack, or both. So yes, so Nandan has mentioned it's C. So that's the correct answer. Option C is the correct answer. If you have say multiple threads, each thing would be running its own set of functions. Even though the code is shared, the the functions that are executed will be different. Functions, the functions or the code executed is different for each thread. It's different, and the stack as the, so the program counter, the PC, and the stack which maintains the call graph, like pushing of the stack and popping those return addresses and all those things. It has to be different, of course, for each thread, and both these things is private for each thread. It will be private, and whenever you do thread switching, this program counter and the stack pointer, though all those things should be where that stack section is located for each thread, those all will be stored in the thread local storage, TLS, when we do thread switching, thread context switch. So option C is the correct answer. The so that's the correct answer. Any doubts in this question, which is not shared by the threads? Uh, okay. So then we come to the last question. Um, if a program has 70% serial code and we have a 5 processor system, 70% serial code, 5 processor system, what is the speed up when compared to the original serial code? Any um, guesses which one is the correct answer? So we use the Amdahl's law. That is 1 by s plus 1 minus s by n. So here we have s equal to uh, 0.7, that is 70%, and n, the number of processes, sorry, the number of cores is 5. So if you just substitute these things, is 0.7. So if 70% is serial code, what's the remaining code? That is parallelized, of course. So that is 0.3. So this is the parallelized version that can be run across multiple processors. And how many processors can we run this 30 percentage of code on? We can run it on 5 processors. And the remaining 70% of the serial code can run it on just a single processor only, since it's just serial code. 30% on the 5 processors we can execute and improve performance, but the 70% serial code on just a single processor. And now if you just okay, 0.3 by 5, 1 by 7 plus, what is this, 0.06, it's 1 by 0.76, and wait, that is 100 by 76. Oh, okay, it comes around 1 point, this is 240, so 1 point, around 1.3 it comes, and looking at the options, the nearest value is 1.31. So 1.31 is the correct answer. Um, the remaining options are wrong. So based on this Amdahl's law, 1.31 is the speed up that you achieve when you have 70% serial code. The remaining 30 is can be parallelized across 5 processor systems. Okay, so this is the speed up. Any doubts in this question? The speed up? No. Okay. So in that case, then that's the end of uh, the live session, the questions that we need to discuss. Um, any doubts till now? Any general queries or something?
Uh, Hello.
Yeah, yes, Nandan.
Like I have a question regarding the locking. So
Yeah,
like if you have time, you can explain it. So w- like my question is that I if a process wants to acquire a lock, or like in the process of acquiring a lock, so
okay.
if the preemption happens, uh, then what will be the case? Will the process like get some extra time share, or like
Oh,
how it
so
will
so
it then?
say it is like the, say like process one is given a time share of 10 units, and now at the exactly at the 10th unit it is within that locking mechanism, is it?
Yeah, yeah,
And now your question is whether okay, I'm in locking mechanism, so I should get extra time to finish it properly and I get the lock, the process P1. That's your question, right?
yeah.
So that's where these atomic instructions come into play. So by having these atomic instructions, right, you won't get extra time share because it becomes a bit complicated, right? If you see, uh, how will there should be some way that this process P1 should communicate to the scheduler, which tells it to stop running, that hey, I am running in this locking mechanism, I am in this locking mechanism, please don't disturb me. If the process is able to convey that message to the scheduler, then it can extend the time share. But usually in those cases, these atomic instructions would be used. So these atomic instructions, or that atomic function, what happens is that only when that function is fully executed, or that instruction is executed, uh, those that locking would be successful. If it doesn't get executed or preempted in between or something, right, then for sure you will be guaranteed that that locking was a failure. So it is designed in such a way that at the 10th unit, if this locking mechanism was starting executing, it will fail only, mostly. It will fail.
Okay.
And what say like in this locking mechanism, it is accessing say some three variables, like one which is setting which variable is locked, one which is setting the status of that variable, whether it's read lock or write lock or something like that. So setting these variables all will happen in a atomic fashion such that either all of these three would be set or it won't be set. And if it gets set, then fine, your locking was success. But if it gets preempted in between or something, right, due to this time quantum 10, those three variables won't be set atomically. That's the importance of having these atomic instructions. It makes designing this locking, the synchronizations very easier, because in software, how much ever you try to design these functions like in an atomic fashion, right? These functions would finally will be like a list of 10 instructions, like 10 assembly instructions. And while executing any instruction out of these 10, the preemption might occur and you won't have control over when that preemption occurs. And when preemption occurs, it is usually difficult to tell the scheduler that wait, it's getting, I'm in a locking mechanism, or it is very hard to communicate to the scheduler, because uh, uh, one thing, right, from a security point of view, why do we have a scheduler in the first place? Because you have multiple processes, say P1 to P10, 10 processes, and the scheduler should be fair, and it should give uh, it should schedule and it should provide the CPU core to each of the 10 processes in an equal fashion. And say if this process P1 is malicious, and if I have a logic such that at the time of preemption, if that currently executing process in this locking mechanism, then that process can tell the scheduler and get some extra time share, something like that. And say at each time when the scheduler wants to preempt P1, it tells the process P1 tells scheduler that I am in a locking mechanism, please extend my time share. Each time if it tells that, then there is the notion of scheduler, like which is fair and um, like fair and well balanced scheduler. It doesn't make much sense. So having this atomic instruction and designing the locking mechanism atomically is the right way to go ahead in this case.
Yeah, thank you. That was helpful.
Okay. Yeah. I will.
Uh,
Yeah.
One more question, like, do you have do you have locking in our syllabus?
Sorry, I didn't get it. Locking in.
Like, do we have locking in our course? Like, I mean,
Locking.
like, locking mechanisms will be taught in our course or not?
Oh, in course.
Yeah, yeah.
I'm sure yes, it will be taught. I didn't check the syllabus,
Okay.
but it will be taught mostly, because locking and synchronization is part of the um, OS. It's crucial to OS at multi-threaded and these things. It will be taught. I will check the syllabus. If not, maybe in one of the upcoming sessions, I can just give like a brief overview of locking. That's okay with you. If it's not taught,
Yeah, thank you. Yeah, yeah.
so I can give a brief overview. So that would be good. And I can give some resources notes also, like pointing to the notes or online links where this locking is well explained also. I can point. That's fine.
Yeah, okay, okay.
Okay. I will. Yeah. Any other doubts? Uh, Nandan or Shashikant, any other doubts you have? If not, then we can end this live session. I will add the doubts that you had all asked during the live session to the end of the slide. Those are all like very interesting doubts, so you can add it and we'll see. So, can we end this session then?
Yes, please.
Yeah. Okay. Thanks, Nandan. It was a very interactive session. I enjoyed it. Thank you.
Thank you for the information. Yeah.
Yeah. Thank you. Thanks, Shashikant.